And now in this lecture we will find out the area of the green shape using two different methods. In the drawing we have two circles. Each circle is passing through the center of the other circle, and we know that the radius of each circle is equal to 5 units, and we want to find out the area of this green shape. Okay, but first of all I will present to you the term segment. Segment is the area inside the circle that is bounded by two radiuses and the arc between those two radiuses, and the area of a segment is equal to pi r squared times the angle between the two radiuses over 360 degrees, when r is the radius of the circle. And in this case the angle between the two radiuses is 60 degrees, therefore the area of this sector AOB is equal to pi r squared times 60 degrees over 360 degrees. Again, sector is the area that is bounded between two radiuses and the arc that is included between those two radiuses, and the area of a sector is equal to pi r squared times the angle between the two radiuses over 360 degrees. And we have also another term, the term segment. The definition of a segment is the area inside a circle that is bounded by chord AB and arc AB. So the area that is bounded by chord and the arc that is attached to that chord is the area of a segment. Is defined as a segment. So here we have segment AB, that is actually the area that is bounded by chord AB and arc AB, and the area of a segment, or the area of this segment AB, is equal to the area of sector AOB minus the area of triangle AOB. Okay, if you subtract from the area of sector AOB the area of triangle AOB, you will get the green shape that is the area of segment AB. Okay, again, a segment is the area that is bounded by a chord and the arc that is attached to that chord. In this case, it is the area that is bounded by chord AB and arc AB. And the area of a segment is equal to the area of sector AOB minus the area of triangle AOB. Okay? So, here we will define the center of this circle as point P. We will define the center of this circle as point Q. We will define the first intersection point of those two circles as point A, and we will define the second intersection point of those two circles as point B. The next step, we will connect together, we will join together points P and B by a straight line. Line segment PB is the radius of this circle. I have to mention that each circle here, the radius of each circle is equal to 5 units, as you can see here. So here, line segment PB is the radius of this circle because of the fact that it starts from the center of the circle, that is to say from point P, and ends at point B. That is a point on this circle itself. Therefore, PB is the radius of this circle, that is to say it equals to 5 units. And we'll join points Q and B together by a straight line. Here, line segment QB is the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point Q, and ends at point B, that is a point on this circle itself. Therefore, QB is the radius of this circle, that is to say it equals to 5 units. Likewise, we will join points A and P together by a straight line. And again, AP, line segment AP, is the radius of this circle because of the line segment AP is the radius of this circle because of the fact that it starts from point P, that is the center of this circle, and ends at point A, that is a point on this circle itself. Therefore, AP is the radius of this circle, that is to say it equals to 5 units. And we will join points A and Q by a straight line. Here, line segment AQ is the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point Q, and ends at point A, that is a point on this circle itself. Therefore, AQ is the radius of this circle, that is to say it equals to 5 units. So here we have quadrilateral APBQ, and all the sides of quadrilateral APBQ are equal to each other, they are equal to 5 units. And any quadrilateral that all of its sides are equal to each other, but all of its angles are not equal to 90 degrees, is defined as a rhombus. So here I write down that quadrilateral APBQ is a rhombus. Quadrilateral APBQ is a rhombus. So we will join points A and B together by a straight line. Actually, AB is the diagonal of rhombus APBQ. In the next step, we will join points P and Q together by a straight line. So here, diagonal PQ, PQ or line segment PQ is the diagonal of rhombus APBQ, but PQ is the radius of this circle because of the fact that it starts from point P and ends at point Q, that is a point on this circle itself. Therefore, PQ is the radius of this circle, that is to say it equals to 5 units. PQ equals to 5 units. And the diagonals of a rhombus has 2 characteristics that are relevant to this question. So I write them down. The diagonals of a rhombus has 2 characteristics. the first characteristic of the diagonals of a rhombus is that they are perpendicular to each other. So here the diagonal AB is perpendicular to the diagonal PQ, and the diagonal PQ is perpendicular to the diagonal AB. Here we will define the intersection point between diagonal PQ and diagonal AB is point M. So those two diagonals perpendicular to each other, that is to say, we will have here 4 right angles. And the second characteristic of the diagonals of a rhombus is that they bisect each other. The diagonals of a rhombus bisect each other. So here the diagonal AB bisects diagonal PQ, that is to say it divides to 2 equal parts. It means that PM equals to MQ. And it is also true to say that the diagonal PQ bisects diagonal AB. That is to say AM equals to MB. AM equals to MB. So we know that PM equals to MQ. So if PM equals to MQ and we will define PM as X, then MQ will be also equal to X, because they are equal to each other. So X plus X equals to PQ from one side. So X plus X is 2X. 2X equals to PQ from one side. But from the other side, we have already found out that PQ equals to 5 units. So from this equation, 2x equals to PQ equals to 5, we will derive that 2x equals to 5. 2x equals to 5. Here we will divide this equation by 2, and we will get that x equals to 5 over 2. X equals to 5 over 2. Here, so we will substitute x by 5 over 2. And here also x equals to 5 over 2. In the next step, we will focus on angles, on 4 angles. Angle APM, triangle APM, the right angle APM. We will also focus on angle MPB. We will focus on angle MQB, this angle, and we will focus on angle MQA. On those 4 angles, actually the cosine of those 4 angles in each right triangle the cosine of each of one of the four angles will be equal to 5 over 2 over 5. I will repeat again. That the cosine of each of the four angles of each one is equal to 5 over 2 over 5. Here 5 over 2 over 5 is 5 over 5 times 2. 5 over 5 is 1, so it is, in conclusion, it equals to 1 over 2. So we found out that the cosine of each one of the four angles inside the four right triangles is equal to 1 over 2, and if the cosine of the angle is equal to 1 over 2, it means that the angle itself is equal to 60 degrees. Okay? It means that the angle itself equals to 60 degrees. Therefore, we actually found out that each one of the four angles is equal to 60 degrees. That is to say, angle APM equals to 60 degrees, angle BPM equals to 60 degrees, angle MQB is equal to 60 degrees, and angle AQM is also equal to 60 degrees. Okay? In the next step, we will prove that those two triangles can go into each other. That is to say, triangle APB can go into triangle AQB. So I write it down. We will prove that triangle APB is congruent to triangle AQB. So why those two triangles can go into each other? First of all, we know that AP equals to AQ equals to 5 units. AP equals to AQ equals to 5 units. I'll repeat again. AP equals to AQ equals to 5 units. We also know that PB equals to BQ and is also equal to 5 units. PB equals to BQ that equals to 5 units also. PB equals to PQ equals to 5 units also. And AB equals to itself. AB equals to AB is a common side that belongs to both triangles. I repeat again. AB equals to AB is a common side that belongs to both triangles. So we actually proved that triangle APB can go to triangle AQB according to side rule. Triangle APB congruent, this is the sign of congruent, to triangle AQB according to side rule. That is to say, we proved that all the sides of triangle APB are equal to all the sides of triangle AQB. Therefore, we proved that those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we will conclude that they have also the same areas. So we will conclude that triangle APB, the area of triangle APB is equal to the area of triangle AQB. Okay? So I write it here that we conclude that the area of triangle APB. I will remind you again that the squared brackets is the same for the area. This means that the area of triangle APB is equal to the area of triangle AQB. Okay? What is the area of sector APB? The area of this sector. The area of sector APB the area of sector APB will be equal to pi r squared times 60 plus 60 is 120. So it is pi r squared times 120 degrees over 360 degrees. I will repeat again, I write it down that the area of sector APB equals to pi r squared times 120 degrees over 360 degrees. R equals to 5 units, R squared is 5 squared, 5 squared is 25, so in the numerator we have 25 pi, and in the denominator we have 120 degrees over 360 degrees is 1 over 3, so we have 3 in the denominator. So we found out that the area of sector AQB, the area of sector APB is equal to 25 pi over 3 square units What is the area of sector AQB? The area of sector AQB is equal to pi r squared times 120 degrees over 360 degrees. I write it down. The area of sector AQB equals to pi r squared times 120 degrees over 360 degrees. Again, it has the same expression exactly as the area of sector APB, therefore it will be also equal to 25 pi over 3 square units. I will repeat. The area of sector AQB is also equals as the area of sector APB, and they are both equal to 25 pi over 3 square units. I will write it down. We actually found out that the area of sector APB is equal to the area of sector AQB. And we have already found out that the area of triangle APB is equal to the area of triangle AQB. If we define the area of those two triangles as x, then we can write here that the area of those two triangles are equal to x according to our definition. And we just right now found out that the area of sector APB equals to the area of sector AQB, and they are both equal to 25 pi over 3 square units. So what is the area of segment APB? The area of segment APB you can see from the drawing that the area of segment APB is this figure that is like a semicircle, but it is not a semicircle. The area of segment APB will be equal to the area of sector AQB minus the area of triangle AQB. The area of sector AQB minus the area of triangle AQB. But we have already found out that the area of sector AQB equals to 25 pi over 3 square units, and the area of triangle AQB equals to x according to our definition. So in conclusion, we found out that the area of segment APB equals to 25 pi over 3 minus x square units. And what is the area of segment AQB? The area of segment AQB you can see from the drawing that the area of segment AQB, it is very similar to a semicircle, but it is not a semicircle. The area of segment AQB will be equal to the area of sector APB minus the area of triangle APB. So it is equal to the area of sector APB minus the area of triangle APB. But we have already found out that the area of sector APB equals to 25 pi over 3 square units. And we have already found out that the area of triangle APB is equal to x according to our definition. In conclusion, we found out that the area of segment AQB is equal to 25 pi over 3 minus x square units, exactly as the area of segment APB, that is, it is also equal to 25 pi over 3 minus x square units. Therefore, we can write down that the area of segment APB is equal to the area of segment AQB. So I'll write it down. We will write down that the area of segment APB is equal to the area of segment AQB. The area of segment APB is equal to the area of segment AQB. And what is the area of the green shape that we are looking for? The area of the green shape the area of this green shape that we are looking for will be equal to the area of segment APB plus the area of segment AQB. So I will write it down. The area of the green shape equals to the area of segment APB plus the area of segment AQB. But because of the fact that the area of segment APB is equal to the area of segment AQB, therefore we can substitute the area of segment AQB by the area of segment APB because they are equal to each other. We'll do it now and we will get that the area of the green shape is equal to the area of segment APB plus the area of segment AQB, but we will substitute the area of segment AQB by the area of segment APB. So we actually found out that the area of the green shape equals to the area of segment APB plus the area of segment APB. That is to say, it equals to 2 times the area of segment APB. Okay, so in conclusion, we found out that the area of the green shape is equal to 2 times the area of segment APB that is to say it equals to 2 times, and the area of segment APB is equal to 25 pi over 3 minus x. So the only thing that is left to do in order to find out the area of the green shape is to find out the value of x. And x is either equals to the area of triangle APB or the area of triangle AQB. They are equal to each other, so we will calculate the value of the area of triangle APB that equals to x. So x equals to the area of triangle APB So we'll calculate the area of triangle APB. We calculate the area of this triangle, triangle APB. The area of triangle APB is equal to the base of the triangle, that is AB. The base is AB, times the height to the base, that is PM, over 2. I'll repeat again. The area of triangle APB equals to the base, that is AB, times the height to the base, that is PM, over 2. So we will find out the value of AB, and we have already found out that AM equals to MB. As you can see here, AM equals to MB. So if we define AM as H, then MB will be also equal to H because of the fact that they are equal to each other. So what is the value of H? We will focus on the right triangle, triangle AMQ. On this right triangle, triangle AMQ, sinus 60 degrees is equal to H over 5 I will repeat again. In the right triangle, triangle AMQ, sinus 60 degrees equals to H over 5. Here we will multiply this equation by 5 and we will get that H equals to 5 times sinus 60 degrees, and sinus 60 degrees is square root of 3 over 2, so we substitute sinus 60 degrees by square root of 3 over 2. So in conclusion, we found out that H equals to 5 times square root of 3 over 2, so I'll write here that H equals to 5 times square root of 3 over 2, and also here H equals to 5 times square root of 3 over 2 units. But as you can see from the drawing, AB equals to H plus H. So here AB equals to H plus H, that is to say AB equals to 2H. So AB equals to 2 times H, and H is 5 times square root of 3 over 2. So in conclusion, AB equals to 2 times 5 times square root of 3 over 2. So 2 over 2 is 1. 2 will get cancelled. And we found out that AB equals to 5 times square root of 3 units. I'll write it here. AB equals to 5 times square root of 3 units, and therefore X, that is actually equals to the area of triangle APB, will be equal to AB times PM over 2. AB, we just found out that AB equals to 5 times square root of 3 units. And as you can see here, PM equals to 5 over 2. PM equals to 5 over 2, all divided by 2. So here, 5 times 5 is 25. So in the numerator, we have 25 times square root of 3. And in the denominator we have 2 times 2, 2 times 2 is 4, So in conclusion, we found out that x equals to 25 times square root of 3 over 4, and the area of the green shape is equal to 2 times 25 pi over 3 minus x I will repeat again. We have already found out that the area of the green shape equals to 2 times 25 pi over 3 minus x, and we just right now found out that x equals to 25 times square root of 3 over 4, so I write it down. We substitute x by 25 times square root of 3 over 4, so it is actually will be equal to 2 times 25 pi over 3 minus x, and x is 25 times square root of 3 over 4. So here we will take out 25 as a common factor of those two expressions, and we will get that the area of the green shape is equal to 2 times, we took out 25 as a common factor. So what is left from 25 pi over 3 after we took from it 25 as a common factor? What is left? It is actually pi over 3. And what is left from 25 times square root of, from minus 25 times square root of 3 over 4 after we took from it 25 as a common factor? What is left? It is actually minus square root of 3 over 4. So the area of the green shape will be equal to 2 times 25 is 50. So it is 50 times pi over 3 minus square root of 3 over 4 square units. I will repeat. The area of the green shape according to the first method equals to 50 times pi over 3 minus square root of 3 over 4 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this green shape according to the second method. Here we'll define the center of this point as point P, as we did in the first method. We'll define the center of this circle as point Q. We'll define the intersection point between those two circles as point A, and we will define the intersection point between those two circles as point B. We will join together points P and B by a straight line. We will join together points A and P by a straight line. We join together points A and Q by a straight line. And we join together points Q and B by a straight line. We have already found out that all those line segments are equal to 5 units, so I will not repeat on it. They are equal to 5 units according to the first method. We will join points P and Q together by a straight line. PQ is also equal to 5 units. It starts from the center of the circle and ends at point Q. Therefore, it is the radius of this circle. That is to say, it equals to 5 units. So here triangle APQ is an equilateral triangle because of the fact that all of its sides are equal to each other, they are equal to 5 units. And in any equilateral triangle, all of its angles are equal to 60 degrees. And likewise, triangle PQ is also an equilateral triangle. All of its sides are equal to 5 units. Therefore, all its angles will be also equal to 60 degrees. It's an equilateral triangle. And so we have here two equilateral triangles. Those two equilateral triangles can go into each other according to side rule. I write it down. Triangle APQ congruent to triangle BPQ according to side rule. So you can see from the drawing, all the sides of triangle APQ can go into all the sides of triangle PBQ. They are all equals to 5 units. Therefore, those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we will conclude that they have also the same areas. So the area of triangle APQ, I will remind you that the square bracket is the sign for the area. It means the area of triangle APQ is equal to the area of triangle PBQ. Because of the fact that they can go into each other, they also have the same areas. Okay? So, what is the area of the green shape? The area of the green shape is equal to the area of the equilateral triangle APQ plus the area of the equilateral triangle PQB plus the area of the four segments, segment AP, segment PB, segment BQ, and segment AQ. So it is plus the area of segment AP plus the area of segment PB plus the area of segment BQ plus the area of segment AQ. I repeat again, the area of the green shape equals to the area of the equilateral triangle APQ plus the area of the equilateral triangle PQB plus the area of segment AP plus the area of segment PB plus the area of segment BQ plus the area of segment AQ. But because of the fact that we have already found out that the area of the equilateral triangle APQ is equal to the area of the equilateral triangle PBQ, here you can see here, we can substitute the area of triangle PQB by the area of triangle APQ. We will do it now, and we will get that the area of the green shape is equal to the area of the equilateral triangle APQ plus the area of the equilateral triangle PQB, but because of the fact that the area of triangle PQB is equal to the area of triangle APQ, we will substitute the area of triangle PQB by the area of triangle APQ, so it is plus the area of triangle APQ plus the areas of segments AP, segment PB, segment BQ, and segment AQ. Okay? So the area of triangle APQ plus the area of triangle APQ is 2 times the area of triangle APQ, so I will write it down. So the area of the green shape will be equal to two times the area of triangle APQ plus the area of the 4 segments AP, segment PB, segment BQ, and segment AQ. Okay, so first of all we have to find out the area of triangle APQ. So what is the area of triangle APQ? Here, in order to find out the area of triangle APQ, we will join together points A and B by a straight line. And we have already found out this point is point M, the intersection point between PQ and AB. We have already found out that AM is equal to edge, that equals to 5 times square root of 3 over 2 units, and MB is also equals to edge, that equals to 5 times square root of 3 over 2 square units. We found it in the first method, so I will not repeat on it. So what is the area of triangle APQ? The area of triangle APQ, the equilateral triangle APQ, will be equal to the base of the triangle, that is PQ, times the height, that is H, over 2. I will write it down. The area of triangle APQ equals to the base of the triangle, that is PQ, times the height, that is H, over 2. So here we have already found out that PQ equals to 5 units. The base equal to 5 units, and we have already found out that H equals to 5 times square root of 3 over 2, and all divided by 2. So here 5 times 5 is 25, so in the numerator we have 25 times square root of 3. In the denominator we have 2 times 2, 2 times 2 is 4. So we actually found out that the area of triangle APQ is equal to 25 times square root of 3 over 4 square units. So we found out the area of triangle APQ. In the next step, we have to find out the area of segment AP. So what is the area of segment AP? The area of segment AP the area of this segment AP will be equal to the area of sector AQP minus the area of triangle AQP. It equals to the area of sector AQP minus the area of triangle AQP. Okay? So here the area of sector AQP, here the area of this sector AQP equals to pi r squared times 60 degrees over 360 degrees. Pi r squared times 60 degrees over 360 degrees minus the area of triangle AQP. We have already found out that the area of triangle AQP equals to 25 times square root of 3 over 4, and here r equals to 2, so r equals to 5. R square is 5 square, 5 square is 25, so in the numerator we have 25 pi, and in the denominator we have 60 over 360 is 1 over 6. So we have 6 in the denominator, so it is 25 pi over 6 minus 25 times square root of 3 over 4 square units. Okay, so I will write it here that the area of segment AP, the area of segment AP is equal to 25 pi over 6 minus 25 times square root of 3 over 4. So in the next step we will find out the area of segment PB. What is the area of segment PB? The area of segment PB is equal to the area of sector PQB minus the area of triangle PQB. So it equals to the area of segment PQB, the area of segment PB equals to the area of sector minus the area of triangle PQB. I repeat again, the area of this segment PQB, equals to the area of sector PQB minus the area of triangle PQB, equals to the area of sector PQB minus the area of triangle PQB. This is the area of segment PB. So the area of segment PB equals to the area of sector PQB, and the area of sector PQB is equals to pi r squared times 60 degrees over 360 degrees. The area of sector PQB equals to pi r squared times 60 degrees over 360 degrees minus the area of triangle PQB. We have already found out that the area of triangle PQB equals to the area of triangle AQB. That is to say, and the area of triangle APQ or QP equals to 25 times square root of 3 over 4. Therefore, the area of triangle PQB that equals to the area of triangle AQP will be equal to 25 times square root of 3 over 4 square units. Here r equals to 5, so r squared is 5 squared, 5 squared is 25, so we have here in the numerator 25 pi, and in the denominator we have 60 over 360 degrees is 1 over 6, so it's 6 in the denominator, so the value of this expression is 25 pi over 6 minus 25 times square root of 3 over 4. So we actually found out that the area of segment PB is equal to 25 pi over 6 minus 25 times square root of 3 over 4, exactly as the area of segment AP. Therefore, we conclude that the area of segment AP is equal to the area of segment PB. So the area of those two segments are equal to each other, and they are both equal to this expression. And if we continue to calculate the areas of segment BQ and the areas of segment AQ, we will find out that the areas of those two segments AQ and BQ is equal to the area of segment AP, or it is equal to this expression that is actually 25 pi over 6 minus 25 times square root of 3 over 4 square units. Therefore, the area of the green shape, so therefore the area of the four segments AP, PB, and BQ and AQ will be equal 4 times the area of triangle AP. The area of 4 times the area of segment AP. Because of the fact that all the segments are equal to each other in their areas, we can take one segment, we will multiply it by 2, and in this way we will get the areas of the 4 segments in total. So therefore we will conclude that the area of the green shape is equal to 2 times the area of triangle APQ plus 4 times the area of segment AP. Because of the fact that if we multiply the area of segment AP by 4, we will get the areas of the 4 segments AP, PB, BQ, and AQ in total. So the area of the green shape will be equal to 2 times the area of the equilateral triangle APQ plus 4 times the area of segment AP. So that is to say, the area of the green shape equals to 2 times the area of triangle APQ. That is to say, it equals to 2 times 25 times square root of 3 over 4. That is the area of triangle APQ plus 4 times the area of segment AP. And we have already found out that the area of segment AP equals to 25 pi over 6 minus 25 times square root of 3 over 4. So the area of the green shape will be equal to 2 times 25 is 50, so this expression equals to 50 times square root of 3 over 4 plus 4 times 25 is 100, so it is plus this expression equals to 100 pi over 6 minus 4 times 25 is minus 100 square root of 3 over 4. So here 50 times square root of 3 over 4 minus 100 times square root of 3 over 4 equals to minus 50 times square root of 3 over 4. And here we have the expression 100 pi over 6. We will divide both the numerator and the denominator by 2. And we will get that 100 over 2 is 50. So in the numerator we have 50 pi. And 6 over 2 is 3. In the denominator we have 3. So here we will take 50 as a common factor out of those two expressions, and we will get that the area of the green shape, according to the second method, will be equal to, so 50 was taken out as a common factor. What left from 55 over 3 after we took from it 50 as a common factor? What is left? It is actually pi over 3. And what is left from minus 50 times square root of 3 over 4 after we took from it 50 as a common factor? What is left? It is actually minus square root of 3 over 4. So in conclusion, we found out that the area of the green shape, according to the second method, equals to 50 times pi over 3 minus square root of 3 over 4 square units. Okay, we finished with the second method. In the next step, I will summarize the lecture. Actually, we wanted to find out the area of this green shape. We found it in two different methods, and I repeat on the question. We have here two circles that each one of the circles is passing through the center of the other circle. The radius of each circle is equal to 5 units, and we want to find out the area of this green shape. So in the first method, I explained to you the term sector. Here this sector AOB, is defined as the area that is bounded by two radiuses and the arc that is included between those two radiuses. So it is the area of the green shape that is bounded by radius AO, radius OB, and the arc AB. and the area of this sector, or the area of any sector, is equal to pi r squared times the angle between the two radiuses over 360 degrees. And r is the radius of the circle, and in this case the angle between the two radiuses is 60 degrees, therefore the area of this specific sector is equal to pi r squared times 60 degrees over 360 degrees, but the area of the sector can be any other, it would be, actually the angle between the two radiuses could be any other angle, therefore the area, the general formula for the area is pi r squared times the angle between the two radiuses over 360 degrees. Okay, again, a sector is the area that is bounded by two radiuses, and the arc between those two radiuses, the arc that is included between those two radiuses inside the circle, and the formula for a sector, for the area of the sector, is equal to pi r squared times the angle between the two radiuses over 360 degrees. Then I explain to you the theorem segment. Segment is the area that is bounded by the chord and by the arc that is attached to that chord. In this case, in this specific case, the green segment is the area that is bounded by chord AB and arc AB, and the area, we will calculate the area of the segment according to the formula that the area of this segment, segment AB, will be equal to the area of sector AOB minus the area of triangle AOB. Okay, you can see that if you subtract from the area of sector AOB the area of this triangle, triangle AOB, you will get exactly the area of this green segment, segment AB. Okay, then in the next step, we defined the center of this circle is point P. We defined the center of this circle is point Q, and we defined the intersection point between those two circles. The first intersection point is point A, and we defined the second intersection point between those two circles is point B. Then we join together points B and Q by straight line. We join together points P and B by straight line. We join together points A and P by straight line, and we join together points A and Q. Actually, each line segment here is the radius of this circle. For example, BQ is the radius of this circle, because of the fact, no, actually BQ is the radius of this circle. Why? Because of the fact that line segment BQ starts from the center of this circle, that is to say from point Q, and ends at point B, that is a point on this circle itself. Therefore BQ is defined as the radius of this circle, that is to say it equals to 5 units. The same thing is true from the other line segments. They are all equal to 5 units. And actually, by drawing those 4 line segments, we created, we have here quadrilateral APBQ that is a rhombus. Why quadrilateral APBQ is a rhombus? Because of the fact that all of its sides are equal to each other. They are equal to 5 units from one side, but from the other side the angles of this quadrilateral are not equal to right angles. They are not equal, all of four of them, to 90 degrees. Therefore, it is not a square, but is a rhombus. That is to say, quadrilateral APBQ is a rhombus. Then we join together points A and B together by a straight line. AB is the first diagonal of rhombus APBQ. We join together points P and Q by straight line. PQ is the second diagonal of rhombus APBQ. And PQ is equal to 5 units. Why? Because line segment PQ starts from the center of this circle, that is to say from point P, and ends at point Q, that is a point on this circle itself. Therefore, PQ is the radius of this circle, that is to say it equals to 5 units. And we have actually two characteristics that is attributed to the diagonals of a rhombus. Here, the diagonals of a rhombus has two characteristics. The first characteristic is that the diagonals of a rhombus are perpendicular to each other. That is to say, the diagonal AB is perpendicular to the diagonal PQ, and the diagonal PQ is perpendicular to the diagonal AB. What does it mean? It means that all four angles here around point M are right angles. And the second characteristic of the two diagonals of a rhombus is that they bisect each other. What does it mean that they bisect each other? The diagonal AB bisects PQ. That is to say, it divides the diagonal PQ to two equal parts. That is to say, PM equals to MQ, and the diagonal PQ bisects diagonal AB, that is to say, AM equals to MB. So because of the fact that PM equals to MQ, we can define PM as X, then MQ will be also equal to X. So what is the value of PQ? PQ will be equal to X plus X from one side. From one side, PQ equals to X plus X. But from the other side, we have already found out that PQ equals to 5. So we have here the equation that 2x equals to PQ equals to 5. So from this equation, we will derive that 2x equals to 5. So here we will divide this equation by 2, and we will get that x equals to 5 over 2. So here x, that is PM, equals to 5 over 2, and here x, that is actually MQ, is also equals to 5 over 2. Then we focused on angle APM, angle BPM, angle BQM, and angle AQM. We focused on those four angles. So in those four angles, the value of cosine of those four angles, it is actually equal to 5 over 2 over 5. Okay, the cosine of those four angles equals to 5 over 2 over 5. 5 over 2 over 5 is 5 over 5 times 2. 5 over 5 is 2, so it is cosine of those four angles equals to 1 over 2. Again, the cosine of those four angles that I mentioned is equal to 1 over 2. And if the cosine of those four angles equals to 1 over 2, it means that the angles, that each angle each angle out of the four angles is equal to 60 degrees. So all the angles here are equal to 60 degrees because of the fact that the cosine of those angles is equal to 1 over 2, and because of the fact that the cosine of those two angles is equal to 1 over 2, it means that the angle itself is equal to 60 degrees. So all the four angles here are equal to 60 degrees. In the next step, we proved that those two triangles can go into each other. Triangle APB can go into triangle AQB. Why those two triangles can go into each other? First of all, we know that AP equals to AP equals to AQ equals to 5 units, AP equals to AQ equals to 5 units, PB equals to BQ equals also to 5 units, PB equals to BQ equals also to 5 units, and AB equals to AB, it equals to itself. That is to say, AB is a common side that belongs to both triangles. So AB equals to AB is a common side. So we actually proved that triangle APB is can go into triangle AQB according to side rule. What does it mean? It means that all the sides of triangle APB can go into all the sides of triangle AQB. Therefore, those two triangles can go into each other according to side rule. Triangle APB can go into triangle AQB according to side rule. And because of the fact that those two triangles can go into each other, we conclude from that fact that they have also the same areas. That is to say that the area of triangle APB is equal to the area of triangle AQB. Okay? So, the area of triangle APB is equal to the area of triangle AQB, and we defined the area of those two triangles as X. Okay? Then, what is the area of sector APB? The area of sector APB equals to pi r squared times 120 degrees over 360 degrees. The area of sector APB equals to pi r squared times 120 degrees over 360 degrees. R equals to 5. R squared is 5 squared. 5 squared is 25. So in the numerator we have 25 pi. And in the denominator we have 120 degrees over 360 degrees is 1 over 3. So in the denominator we have 3. So in conclusion, we found out that the area of sector APB equals to 25 pi over 3 square units. Likewise, we found out the area of sector AQB. What is the area of sector AQB? The area of sector AQB equals to pi r squared times 120 degrees over 360 degrees. The area of sector AQB equals to pi r squared times 120 degrees over 360 degrees. So we have here the same expression as we got here. Those two expressions are equal. Therefore, the area of sector APB will be also equal to 25 pi over 3. So we found out that the area of sector APB is equal to the area of sector AQB, and those two areas, they are equal to 25 pi over 3 square units. And we also found out that the area of triangle APB is equal to the area of triangle AQB, and they are equal to X according to our definition. What is the area of segment APB? Segment APB is this shape that is like a semicircle, but it is not a semicircle. So the area of segment APB, this figure that is like a semicircle, will be equal to the area of sector AQB minus the area of triangle AQB. Okay, the area of segment APB equals to the area of sector AQB minus the area of triangle AQB. We have already found out that the area of sector AQB equals to 25 pi over 3, and the area of triangle AQB equals to X according to our definition. So in conclusion, we found out that the area of segment APB equals to 25 pi over 3 minus X square units. Likewise, we calculated the area of segment AQB, the area of this figure that is similar to a semicircle but is not a semicircle. The area of this segment AQB will be equal to the area of sector APB minus the area of triangle APB. Okay, the area of segment AQB equals to the area of sector APB minus the area of triangle APB. But we have already found out that the area of sector APB equals to 25 pi over 3 square units, and the area of triangle APB equals to X. So in conclusion, we found out that the area of sector APB is equal to the area of sector AQB. Okay? We found out that the area of sector APB is equal to the area of sector, the area of segment APB. Here we found out that the area of segment APB is equal to the area of segment AQB. Okay, those two expressions are equal to each other, therefore those two segments are also equal to each other. Again, the area of segment APB is equal to the area of segment AQB. So what is the area of the green shape? The area of the green shape equals to the area of segment APB plus the area of segment AQB. The area of the green shape equals to the area of segment APB plus the area of segment AQB. Okay? But because of the fact that the area of segment APB is equal to the area of segment AQB, we can substitute the area of segment AQB by the area of segment APB because they are equal to each other. So we did it here and we got that the area of the green shape equals to the area of segment APB plus the area of segment APB. That is to say, the area of the green shape equals to 2 times the area of segment APB. Okay? Again, the area of the green shape equals to 2 times the area of segment APB. And we have already found out that the area of segment APB equals to 2 times 25 pi over 3 minus x. So the only thing that is left to find in order to find out the area of the green shape is to find out the value of x. And the value and x is defined as the area of triangle APB. So x that equals to the area APB, the area of triangle APB is equal to the base of the triangle that is AB times the I to the base that is PM over 2. Again, x that equals to the area of triangle APB equals to the base of the triangle that is AB times the I to the base that is PM over 2. What is the value of AB? Here we focus on this right triangle, triangle AMQ. Here sinus 60 degrees equals to edge over 5. Sinus 60 degrees equals to edge over 5. We multiplied this equation by 5 and we found out that edge equals to 5 times sinus 60 degrees. And sinus 60 degrees is square root of 3 over 2. So in conclusion, we found out that edge equals to 5 times square root of 3 over 2. But AB itself equals to edge plus edge. So that is to say, AB equals to edge plus edge, that is 2 edge. So AB equals to 2 edge, and edge equals to 5 times square root of 3 over 2. So 2 times edge is this expression. Here 2 over 2 is 1. So in conclusion, we found out that the length AB is equal to 5 times square root of 3 units. AB equals to 5 times square root of 3 units. Therefore, x that equals to the area of triangle APB that equals to AB times PM over 2, that is the base times the height over 2. Here AB equals to 5 times square root of 3. PM is equal to 5 over 2. So it is 5 times square root of 3 times 5 over 2, all divided by 2. So here we have 5 times 5 is 25. So in the numerator we have 25 times square root of 3, and in the denominator we have 2 times 2, that is 4. So in conclusion, we found out that x equals to 25 times square root of 3 over 4. So here x equals to 25 times square root of 3 over 4. So the area of the green shape equals to 2 times 25 pi over 3 minus x. So it is 2 times 25 pi over 3 minus x, and x equals to 25 times square root of 3 over 4. So the area of the green shape equals to this expression. So here we took 25 out of those two expressions as a common factor, and we got that the area of the green shape equals to 2 times 25, and what is left from 25 pi over 3 after we took from it 25 as a common factor. What is left from it is pi over 3. What is left from 25 times root of 3 over 4 after we took from it 25 as a common factor? What is left from it is actually minus square root of 3 over 4. So in conclusion, we found out that the area of the green shape equals to 2 times 25 pi over 3 minus square root of 3 over 4. 2 times 25 is 50. So in conclusion, we found out that the area of the green shape according to the first method is equal to 50 times pi over 3 minus square root of 3 over 4 square units. We finished with the first method. Then I presented to you how to find out the area of the green shape according to the second method. In the second method, we did the same construction as we did in the first method, and here we note that all the 9 segments here are equal to 5 units. So here triangle APQ is an equilateral triangle. That is to say, all of its sides are equal to each other, they are equal to 5 units, and all the angles inside in the equilateral triangle are equal to 60 degrees, so all the angles here are equal to 60 degrees. Likewise, triangle PBQ is also an equilateral triangle, therefore all of its angles will be also equal to 60 degrees here. All the angles are equal to 60 degrees. And here, the equilateral triangle APQ is congruent to the equilateral triangle PBQ. And because of the fact that those two triangles can congruent to each other, we will conclude that they have also the same areas. That is to say, the area of triangle APQ is equal to the area of triangle PBQ. And what is the area of the green shape? The area of the green shape equals to the area of triangle APQ plus the area of triangle PBQ plus the area of the 4 segments AP, PB, BQ, and AQ. I'll repeat again. The area of the green shape equals to the area of triangle APQ plus the area of triangle PBQ plus the area of the 4 segments AP, PB, AP, BB, AP, PB, BQ, and AQ. Okay, but because of the fact that the area of triangle APQ is equal to the area of triangle PBQ, as we found here, we can substitute the area of triangle PBQ by the area of triangle APQ. We did it, and we got that the area of the green shape equals to the area of triangle APQ plus the area of triangle APQ plus the area of the 4 segments AP, PB, BQ, and AQ. So the area of the green shape equals to the area of triangle APQ plus the area of triangle APQ is 2 times the area of triangle APQ plus the areas of the 4 segments AP, PB, BQ, and AQ. So what is the area of triangle APQ? The area of this triangle APQ, equals to the base of the triangle that is PQ times the height that is H over 2. Okay? And the area of triangle APQ equals to the base PQ times the H that is times the height that is H over 2. We have already found out that PQ equals to 5 units. H, we found in the first method that H equals to 5 times square root of 3 over 2. So it is 5 times square root of 3 over 2, all divided by 2. So the area of triangle APQ equals to 5 times 5 is 25. So in the numerator we have 25 times square root of 3 over 4. So in conclusion, we found out that the area of triangle APQ equals to 25 times square root of 3 over 4. And that is the area of triangle APQ. In the next step, we have to find out the area of segment AP. What is the area of segment AP? The area of segment AP equals to the area of sector AP minus the area of triangle. The area of segment AP equals to the area of sector APQ minus the area of triangle APQ. The area of segment AP equals to the area of sector AQP minus the area of triangle AQP, and the area of sector AQP equals to pi r squared times 60 degrees over 360 degrees. And we already found out that the area of triangle AQP equals to 25 times root of 3 over 4. R equals to 5, so r squared is 5 squared. 5 squared is 25, so in the numerator we have 25 pi, and in the denominator we have 60 degrees over 360 degrees is 1 over 6, so we have 6 in the denominator. So the value of this expression, it is actually 25 pi over 6, and minus 25 times root of 3 over 4. So the area of segment AP equals to 25 pi over 6 minus 25 times root of 3 over 4. Then, so the area of segment AP equals to 25 pi over 6 minus 25 times root of 3 over 4. Then we found out the area of segment PB. What is the area of segment PB? The area of segment PB equals to the area of sector PQB minus the area of triangle PQB. Here, the area of segment PB equals to the area of sector PQB minus the area of triangle PQB. The area of sector PQB, the area of this sector, equals to pi r squared times 60 degrees over 360 degrees. And the area of triangle PQB, we know that the area of triangle PQB is equal to the area of triangle APQ. And we have already found out that the area of triangle APQ equals to 25 times root of 3 over 4. That is to say, the area of triangle PQB equals also to 25 times root of 3 over 4. So here pi r squared, r is equal to 5, so r squared is 5 squared. 5 squared is 25, so in the numerator we have 25 pi, and in the denominator we have 60 degrees over 360 degrees is 1 over 6. So in conclusion, the value of this expression is 25 pi over 6. So in conclusion, we found out that the area of segment PB equals also to 25 pi over 6 minus 25 times root of 3 over 4. That is to say, the area of segment AP is equal to the area of segment PB. And if we continue to calculate the area of segment BQ and calculate the area of segment AQ, we will find out that they are equal to this expression that is actually 25 pi over 6 minus 25 times root of 3 over 4. That is to say, the area of all 4 segments are equal to each other, and they are equal to this expression. That is to say, it equals to the area of segment AP. Therefore, the area of 4 segments, the 4 segments in total, AP, PB, PQ, and AQ, will be equal to the area of segment AP times 4. Therefore, the area of the green shape will be equal to the area, to 2 times the area of triangle APQ plus 4 times the area of segment AP. Why? Because all the segments are equal to each other. So if we multiply the area of one segment by 4, we will get the area of the all 4 segments in total. Therefore, the area of the green shape equals to 2 times the area of triangle APQ plus 4 times the area of segment AP. So the area of the green shape equals to 2 times the area of triangle APQ, and we already found out that the area of triangle APQ equals to 25 times root of 3 over 4, and plus 4 times the area of segment AP, and the area of segment AP equals to 25 pi over 6 minus 25 times root of 3 over 4. So the area of the green shape equals to this expression. Here, with 2 times 25 is 50, and here 4 times 25 is 100, so here we have the expression 100 pi over 6, and here 2 times minus 25 is minus 100, so here we have the expression minus root of 3 over 4, so the area of the green shape equals to 50 times root of 3 over 4 plus 100 pi over 6 minus 100 times root of 3 over 4. 50 times root of 3 over 4 minus 100 times root of 3 over 4, it equals to minus 50 times root of 3 over 4, and the expression 100 pi over 3 We divided both the numerator and the denominator by 2. 100 over 2 is 50, and 6 over 2 is 3. So in conclusion, we got that the area of the green shape equals to 50 pi over 3 minus 50 times square root of 3 over 4. Here we took 50 as a common factor out of those two expressions. So the area of the green shape equals to 50. 50 was taken as a common factor. So what is left from 50 pi over 3 after we took from it 50 is a common factor? What is left from it is pi over 3. And what is left from the expression of minus 50 times square root of 3 over 4 after we took from it 50 is a common factor? What is left from it is actually minus square root of 3 over 4. So in conclusion, we found out that the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units. And it is exactly the same result as we got in the first method. Okay, thank you very much.